I cannot click. How do I do this? Sorry, give me 1 second so I can press got it, because otherwise my mouse. Okay, so I'm going to talk mostly about 2 projects that I've been working on with really closely with Rene Gertsma, also at University of Amsterdam. And so with Rene, we have been thinking about how to combine the trapped ion platform with optical tweezers to both make more programmable analog simulators, and also create easier like sort of infrastructurally more simple 2-qubit gates that will let us maybe have a better and more scalable architecture for a trapped ion quantum computer. So I guess the audience here, a lot of people at QSoft think a lot about quantum algorithms, and they say that, okay, if you have a quantum computer, then you would like to execute quantum algorithms that are much more efficiently done on a quantum computer. But there's a sort of, from a physics point of view, what we want to do is we want to be able to simulate physics. And a lot of the problems, of course, that are hard computationally, you can of course map them also to spin models that are hard to simulate and to understand. And the idea is here that we want to build, in the analog case, a scale model of something that is much harder to understand. So here's my excellent cat, and my cat can tell me a lot about a wilder cat that is less controllable. And in the case of quantum simulation, now you have access to a lot of different AMO systems, and you use them to basically understand both equilibrium phenomena and also out of equilibrium dynamics of the system. And the out of equilibrium part maybe is really of interest now, because you can use it to, for example, prepare very highly entangled states that are useful for quantum information purposes and for quantum metrology, but also they really let you understand fundamental physics related to thermalization or lack thereof in systems and entanglement dynamics. And then there is also, of course, the original idea of using quantum simulation to understand equilibrium phenomena. So this is more like criticality or the phases of matter and so on. Trapped ions let us do both analog simulation and digital simulation. So they both let you create maybe like a more controllable version of the system that you want to study. But now this might be more limited in a sense, like the number of programs the simulator can run are limited, but that the simulator is particularly well suited to that type of problem. So it will be very efficient. Or it can be a digital simulator that's much more flexible, but then you might not be particularly good at a particular set of problems, basically. So the idea of a trapped ion quantum computing comes from because you have access to these ions that have very long coherence times. So in René's group at UvA, and also in other groups, so this is like Chris Monroe's group, they use the ytterbium ion. It has very long coherence times because of the way, and I'll show you that you engineer interactions in these systems, you can have fully connected systems. So the interactions between your qubits come from collective motion of the ion crystal. And it's one of the most developed platforms for both quantum computing and quantum simulation. So what we wanted to do was, we had 2 goals, basically. We wanted to combine this platform with tweezer potentials to both be able to have more tunable interactions, but also to basically have new gate architectures. So I'll first do the sort of the interaction part, and then I'll switch and talk about a new type of 2-qubit gate. Okay. So to understand how the interactions in these types of systems work, you can consider, for example, so a 1D chain of ions. And in principle, when you have ions in a trap, there's competition between the Coulomb repulsion between the ions, but also with the trapping potential that your trap supplies. And this competition makes the ions form a crystal. And this crystal of the ions is now sort of a Coulomb crystal that can be in 1 dimension or 2 dimension, or it can be a 3D crystal, depending on the type of potential that you have supplied and what geometry becomes stable for this crystal then. You always have ions that you can select 2 of its levels to use as qubits. And then here you can see, for example, a simulation where you have 12 of these ions and they form a 2-dimensional crystal due to the trapping parameters that you have set, where you have very strong trapping in 1 direction, but less strong trapping in the Y and Z direction. And because of this, you form this 2-dimensional crystal. Okay, so now to understand how the interactions come about, and these interactions are important both in the gate case. I mean, all these like Molmar-Sorensen type gates, they use these, and also just in the normal simulator also. Yes.
Can I ask a question?
Yeah.
So you assemble the ions into a Coulomb crystal.
Yeah.
Can you say a little bit more about how does that work exactly?
Yeah. So you always have.
Is there like, I mean, I'm sort of a theoretical computer scientist, so I have no knowledge of these things. I barely know what an ion is, but I've seen these ion traps in Innsbruck, for example. And is this, I mean, but there's like typically 1 ion in the trap, or no, actually I don't know. So is this in 1 trap or is this in multiple traps?
It's in 1 trap. So you can have, for example, you can have 1 trap, and then in this 1 trap, you will have a particular sort of time varying electric field, for example. And then this generates a potential for the ions that generates a stable, that allows you to have a stable configuration. So, but then the point is that you have this potential that wants to confine the ions, but then you have the Coulomb potential between the ions that wants the ions want to repel each other. And the balance of these things creates this crystal structure. But then there are different ways. The ones at Innsbruck, I guess, they use these, they use electric fields, but there's a different type of, different idea where you can use a magnetic field. And then you also have this ion plasma that rotates and then experiences Lorentz force.
What I remember, there are like 2 types of traps. One is a penning.
Yeah, exactly. In the penning, you use a very strong magnetic field. And then you also have this rotating wall potential, but basically you have ions that are rotating, and then they experience a Lorentz force, and that gives them a confinement. So you have both electrodes and the giant magnetic field.
And it doesn't matter which kind of trap, you can all do it in both?
Yeah, I think in the penning trap, it's usually you have a 2D crystal, and then you have you have an instability that makes you go from 2D to 3D crystal. And in the Paul traps, typically people have done 1D chains, but you can also have 2-dimensional crystals. Penning traps are, I think, more, well, at least the one I know is much more stable with many ions. So it's actually harder to have a small crystal. And with the Paul traps, I think it's not a problem. You can have, I mean, I think it's easier actually to have a smaller little bit crystal.
And it's a 2-dimensional crystal here.
Here we are going to consider a 1D and a 2D chain, but it doesn't, to some extent, it matters a little bit in terms of simulation, but not too much, because the dimensionality is separate from the connectivity in these models. So a little bit, I think, because your interactions come from the mode structure, to some extent, it doesn't matter too much what the dimensionality of the system is, because the phonons that mediate the interaction, you can engineer the connectivity such that effectively you have a higher dimensional system, even though physically you're in 1D, I guess.
Okay, thanks.
Okay, so you have, okay, so now the way you understand how the interactions come about is if you look at the vibrations of the ions about their equilibrium position. And this is, you remember maybe when you did phonon modes of a crystal, and this is the same idea. So now you have trap potential. So here, that's the, sorry, I cannot find the point. I cannot see my mouse, so I don't know how to point. But on the first term that you see on the left-hand side is the trap potential. And then you have a second term, which is this Coulomb repulsion between the ions. So that's what the full potential that each of the ions feels. And then you can solve for this phonon modes of the crystal. And if you have if you have n ions, you'll have in 3 n modes. Each mode is specified now by its frequency and by its eigenvector. So the eigenvector tells you the amplitude of the mode at the position of each ion. And so here you see this is omega, and the normal mode itself is this a boldface B. And then you can solve now for the phonon modes of the crystal. And you can look at what they look like, and you see that there are modes that are in plane and there are modes that are transverse to the plane of your crystal. So the number 6 that I'm showing is a particular mode. You see everything is moving together, and there is no, the distance between the ions isn't changing. But then mode 25, the distance between the ions does change, and it's much higher energy. Okay, so what do we do with these modes? What we do is now we use a particular scheme called the Raman scheme to basically excite these modes. And you can select which modes you excite and you strongly couple to by tuning the beat note frequency between the 2 laser beams. And sort of if you're close to one of the modes or some of the modes, you mostly couple to those. If you're very far away from everything, you weakly couple to everything. Okay, and then, yes.
May I also ask a question? I think, so a couple of slides ago, you said you can solve for the modes depending on this potential.
Yeah.
Does that mean you figure out the states that minimize the energy? How do you solve?
Initially, yeah. So initially you solve the equilibrium configuration by that kind of, yeah. So you find the configuration that minimizes the energy, and that's your equilibrium. And then you solve for the small vibrations around the minimum. And so that requires, then you construct a Hessian, and the Hessian tells you what the modes are in this harmonic approximation to the potential. Yeah, so you expand your potential around the equilibrium positions of the ions, because you say my ion oscillates only a little bit around this equilibrium position. And those are the modes that you're solving for.
And that's how you get the configurations on the next slide.
That's how you get yes, that's how you get these modes. Yeah, exactly.
Okay, thanks.
Okay, so now to understand how the ion-ion interaction comes about is it's easier to first consider only if you couple to one mode. So if you couple particularly to a mode that's uniform across your crystals, like that looks like a center of mass mode, then you can write a Hamiltonian that, so you can see that the internal state of your ion couples only to this mode. So this is the phonon position operator, and this is the total spin. The reason you get the total spin is that all of the ions couple the same way to this mode. So everything becomes collective. And then if you look at what this type of Hamiltonian does, it basically creates a Hamiltonian that in quantum optics people call single axis twisting, but it's basically just an Ising model that is all to all. So all the spins couple to all the spins with the same strength. And the strength that you couple to depends on the strength of the coupling between the internal state of your qubit and the phonon mode and the detuning you have from this mode. So you can see, for example, that what this type of Hamiltonian is supposed to do. If you start in a separable state that has no entanglement and you act on it with this type of Hamiltonian, it generates entanglement and it generates this thing called a squeeze state. And the great thing about this type of Hamiltonian is that it's simple enough that you can also in a system benchmark it really. So you can run it in a trapped ion simulator, and you can calculate what you should get, including all the sources of decoherence and sort of imperfections in the experiment, and then compare to the experimental measurements and understand your system a bit better, right? Okay, so here you can see, for example, that what we're measuring is the same model, and what we're measuring is if I start initially with n spins all pointing on the x direction, and I measure what happens as time goes on, then I change my size of my spin-spin interactions, then I can basically calculate theoretically what I should get, and also the sort of points are the experimental data. Okay. All right. So now, what in general, however, if you try to use all of the modes in your crystal, you still have something that looks like an Ising model, but now the spin-spin coupling is now going to depend on all the modes that you have at their amplitudes, all the mode frequencies, and then also how strongly each mode contributes, which as I was saying, depends on how close the beat node frequency is to the mode frequency. And then if you do that, we want to know, so typically when people, okay, so the modes that naturally occur in the crystal, typically when people do this, you're restricted to interactions that decay like a power law. So it's a 1/r types of interaction, and the power law is either all to all or it's like around 1/r cubed. But what we wanted to know was, can we do a bit better than this? And the point, what I'm going to show you is that you will still be restricted to a family of models. So now, for example, it will be still Ising type, like, so it would be well, not Ising, but it would be still 2-qubit interactions, but now you can make a bigger family of them. So you won't be restricted to this parallel types of decay, okay? So the way you do it now is we wanted to use these local optical potentials. And what we do is we add this local optical potential now. So this is the tweezer onto the potential that we had before. So here you can see on the term that I added. Now this is just a harmonic confinement additional that comes from the tweezer, okay? And then, okay, so now what we do is we now solve for the new phonon modes and the new mode frequencies, but also we keep in mind that the tweezer that we apply locally is tunable. So we can do sort of apply different potentials at different locations in the lattice. And then what we want to do is we want to have a target interaction matrix and then find the tweezer pattern that generates that target interaction matrix. And we can, so the student who worked on this found, first of all, a feasibility test. So given a particular target matrix, can we do it using the optimization space that we have? So we can first find, so we can basically find out, given a particular target J, whether, and can we find a tweezer pattern that actually generates that target J. So if this test is satisfied, then we can actually start looking for our target J. And so here you can see some examples where we try to find, for example, instead of these very long range interactions, now the opposite. So we say, can we use the tweezers to make nearest neighbor interactions? So now every ion in the chain only acts with the one next to it. And you can see that when you add the tweezers, now the modes are shifting from this red ones that I'm showing on the plot of mode versus frequency to the green ones. So they're shifted quite a bit. The tweezer pattern you can see above, so that's the ion chain, and you can see that the potential that you're applying on each of the ions. And then and the resulting coupling matrix is shown also at the bottom. We can try a little bit more ambitious models. So if you have a 2-dimensional crystal and we want to look at frustration in these systems, so then you need to have this ferromagnetic, antiferromagnetic coupling on the rungs versus the legs of the ladder. I think that's correct terminology. And we again can find the tweezer potential for that. And so here the green lines are showing the residual errors in the optimization that we have found. And you can see that sort of the error is roughly 10%. And this sort of coincided with similar proposals from two other groups. But now we thought, okay, this is kind of a nice application. Can we make sure that it's also a robust type of setup? And for this, we had students, so Leon Bond, and we had another bachelor student, Lisa Lenstra, who combined, who made sure that basically various effects that usually can kill your schemes. So this is like if you have micromotion or if you have misalignment in the tweezers, that these are effects that your scheme can be robust to. So that was a good check. And we also can even do more complex models, which require sort of tweezing out some of the ions so they don't participate in the interaction. Okay, so that's sort of the first part of this talk. So I showed that if you combine the tweezer with Paul traps, you can control the types of interactions and connectivity that you have in your lattice. But now the second thing we want to consider was, can we use the tweezers for something else? And the something else in this case was we wanted to make a 2-qubit phase gate that was easier to do compared to the typical Molmer-Sorensen type of proposal. So to understand what exactly we want to have advantage-wise compared to the Molmer-Sorensen, if you remember the Hamiltonian I showed you that showed the coupling between the mode and the internal states of the ion, you can now think about if you have 2 qubits, and what this type of Hamiltonian does is that it lets you flip the internal state of a qubit while simultaneously changing the motional state. So there are these multiple paths available to you for the up states, down, down, up, down, and down, up. And then you can also see the motional states that are shown here. So you either are changing the motional state by +1 or by -1. And each of these paths has some amplitude and they interfere with each other. And what happens is that once they have interfered with each other, the dependence on the motional quantum number in principle cancels out. And what you end up with is an Ising type of interaction. So you have a sigma z interaction. And that's what you need to actually make a 2-qubit phase gate so that your up, up, down, down, up, down, and down, up get different phases. Up, down, and down, down will get the same phase, and then the other two get a different phase, and that gives you the phase gate. And then, but what this type of gate relies on is something called a Lamb-Dicke regime, which means that you only allow excitations like I showed you where the motional state changes by 1. So I was only showing pathways where you would flip a spin and increase or decrease the motional quantum number by 1. It also relies on rotating wave approximation, which just means that some of the terms in your Hamiltonian, you consider them to be quite off resonance. So these are usually terms that are oscillating at a very high frequency compared to other terms in your Hamiltonian. And they are terms where you flip a spin up and you also increase your phonon population, or you flip the spin down and you decrease the phonon population as well. So these are the rotating wave, counter-rotating terms. Okay, so what we wanted to do was to sort of have a gate proposal that was a bit more lenient. And in principle, also, we know that when the ion chain gets longer in the Paul traps, it's hard to maintain the interaction strength between the distant ions. So we also wanted to have a scheme that possibly didn't have this problem. So it was scalable enough and you didn't the gate sort of time and the gate time would be independent of the distance between the ions. And also that when you have larger and larger ion chains, you have more degrees of freedom, and you might make errors by entangling erroneously these degrees of freedom. And so we wanted to have a new type of architecture that would allow us to overcome this. We wanted to not have the Lamb-Dicke requirement, and we wanted to have a gate that was simpler infrastructurally. And by that, I mean maybe require less lasers, require less stable lasers, and so on. So something that would be simpler to implement. And for this, what we decided was, okay, we're going to use state-dependent tweezers. So now we want the tweezer potential that I showed you before. I mean, the local optical potential that looked like a Gaussian. I want it to be different for depending on the internal state of the qubit. And the reason you want this is because you still need to generate a force, generate a term that looks like sigma z in the end to get your phase gate. And usually these terms come about from having a spin-dependent force, okay? So you can sort of label these qubit states. Don't label them by, I said by J, but imagine label them by P, because otherwise it becomes confusing because J now, yeah. So I'm gonna use P, and I made a mistake here, I don't change it, okay? So then the potential for the tweezer, you can write that it depends on the, okay, it depends on various things. And there are things that you can basically tune to make sure that you in the end up with a particular tweezer potential experimentally that has this dependence on your internal state. So here you see the tweezer Hamiltonian that I will end up with is a harmonic confinement, but now the harmonic confinement depends on the sigma z of the ion, right? Whether the spin is up or down, it changes the potential from this, or like a harmonic or like a harmonic that is downwards, okay? And now I am considering only two ions. So this is I'm applying tweezers only to ion I and to ion J, okay? And then at this point, I've made no Lamb-Dicke approximation, of course, because this is really the potential that the ion feels. And then what you can do is that we assume we are in a limit where the tweezer potential is very weak compared to the phonon mode frequencies that the crystal has. And then in this limit, what you can see is that, for example, if you have now the center of mass mode, if your ions are both facing up or both facing down, they will have a shift in their frequency. But if your ions are up, down, or down, up, this total spin term, sigma zi plus sigma zj, is 0. So because of that, they will not experience no shift to their oscillation frequency. So this gives us a, okay. So this means that basically the tweezers shift the center of mass mode frequency for two ions in a spin-dependent way. But the spin-dependent is sort of in a 2-qubit state-dependent way, okay? And then the second ingredient is that we also add an electric field. It's a homogeneous electric field. And if you have a homogeneous field, it can only excite modes where all the ions move together. Because if you need to excite other modes, you will need to apply a force that would change the distance between the ions, right? So a homogeneous field doesn't change the distance between the ions, and because of this, it can only excite a center of mass mode. So this means that you have a really easy way of making sure that only the center of mass mode will participate in your dynamics because of this electric field application. So now we can also write what the electric field Hamiltonian does. Sorry. And here we tune the electric field close to the original center of mass frequency. And because of this, it only couples strongly to the 2-qubit states where the qubits haven't shifted. And so they're anti-parallel to each other. And so we want to see whether this will make us the gate that we want, the total Hamiltonian. And we can do a whole bunch of unitary transformations to convince ourselves that some term like this pops out and that this gives us a phase gate. but also we could, and the typical gate time that we get will be of the order of millisecond, but we can also actually do the simulation and make sure that it does, and it is more convincing and maybe more easy. So here you see that the actual gate sequence is a bit more complicated, and this is because there are still sort of higher order effects that I didn't talk about that you will have to sort of correct for. But as you can see, the 0, 1 and the 1, 0 states, and so this is in B, and on the left-hand side, they really couple very strongly to the electric field, so they move a lot in phase space, whereas the 1, 1 state, the 0, 0 states, which are not affected by the electric field, don't move at all. The phase that you accumulate depends on the area that these circles actually enclose. So you can see then that really the 1, 1 and 0, 0 will not get the phase, whereas the 1, 0 and 0, 1 states will acquire a phase if you time it correctly. So here we calculated the process fidelity of this gate as a function of the tweezer confinement, and also the different curves are now the different detunings, and also so they also include sort of two different things. So one is that we want to understand what the effect of thermal phonons are. So this is now the blue squares, the orange circles. So the orange circle is now hotter, but also the detuning is larger. So that means the gate is going to be faster. And then in the other case, and the purple stars are if you basically are very bad at cooling your crystal, then that's what it is. And then you can also, in principle, for 2 ions, you have 2 vibrational modes. So the pentagons now include the spectator mode as well, and show that really the spectator mode doesn't participate and doesn't degrade your fidelity. So we can see that we can really get to 10 to the minus 6 or so in terms of infidelity, and that's really great. And you can at that point, I mean, yeah, do error correction. So that's nice. And also we looked at the scalability of this particular gate. So, I mean, computationally, this is quite hard to have 4 ions and 4 phonon modes and to keep everything. So to go more than 4, it's a little bit hard, but for 4, we saw that basically it made no difference, the fidelity. It was not dependent on where the ions were in the chain. So we show that this is really a scalable type of gates architecture. And then we can also look at, for example, if we have different types of noise in this system, what happens to the fidelity. And of course, if you have a noise that happens to have basically so that it is a slow enough noise that it is of the order of your gate time, then you'll end up really degrading the fidelity of the gate. But you can also have DC noise, and then that really doesn't affect the fidelity of the gate. So sorry, so this was the, yeah. So we now have a new scalable universal gate scheme that uses these tweezers and electric fields. It's not reliant on the Lamb-Dicke approximation, and it's scalable. We have other ideas. So in particular, with Robert Spiriou, also at UvA, we have a different way of now realizing the same type of gate and actually in an even easier setup using the optical Magnus force. And also we have ideas about how to go beyond this perturbative tweezer regime, where I use the fact that the tweezer potential was weak compared to the confinement. That was the sort of the harmonic confinement of the trap. Okay, and now I'm gonna be very out of my depth and just show you some slides that are actually the system that is in René's group. So these are slides that Matteo made. And so we already have everything at UvA. So we have the ion trap, which is a titanium trap that has been gold plated. We have the vacuum setup that this trap goes into. And then we also have all the optical setup, which is required for sort of both cooling the ion and also sort of reading the ions and initializing the ions. So all of these things are already built. Matteo has also characterized the trap with ytterbium 174, has managed to create the 2D crystal, has added in the tweezers and trapped the 171, the qubit ion. And the only thing that's sort of left to do is to really do subdoppler cooling. So that means that then the population of these motional modes that we want to use will be close to the ground state. And also we want to now try really modifying the phonon spectra using the tweezers and also try to make the gate. So thank you for listening. And I'll just highlight that a lot of this work was done by Matteo. So Matteo has done both the theory for the gate and also is in the lab. And this is of course René, who leads the experimental effort. Rima is the postdoc. And this is Juan, and who did the sort of more tweezers to engineer more interesting interaction part of the project. And my student Liam has also looked at the micromotion's role and how robust the proposal is to micromotion. So thank you.